Okay, we are almost done with this lesson. We just had one little thing to talk about, and that was using the Nernst equation when you have concentrations that are not equal to one another. So we looked at this problem right here where we had two concentrations that were equal to one another. So for instance, if you had like your battery and you have a strip of zinc metal and you have a strip of copper metal. So we wrote out our half reactions for this battery. Okay, so we had this, and then we had zinc forming Zn 2 plus 2 electrons. And that gave us these values right here. And then because this one was flipped, that made both of these positive, which if it's a galvanic cell or a battery, they do have to add up to be a positive value. Okay, so volts, joules per coulomb. All right, so these were our half reactions here. So what we have is we have Cu, this is in solution, so these are ions in solution, plus zinc, forming Zn2 plus Cu. Reduction at the cathode, oxidation at the anode. Make sure you know those. So if we have our battery, okay, and our anode is a strip of zinc metal, so we have a zinc solid, and at our anode we have our zinc solution. Okay, and then we have our copper metal for our cathode, reductions at the cathode. So we have copper metal at the cathode, and we have our copper ions in solution. This is just a little bit of a review of voltaic cells. Okay, so it's going to go, our flow is from the anode over to the cathode. Okay, so that's always the direction, anode to cathode. And so what's happening here is zinc is losing those electrons, and when it loses the two negatives, it forms a positive 2. And then over on the cathode side, you have Cu2 plus that's gaining those electrons to form your copper metal. And then, of course, don't forget your salt bridge. That prevents a buildup of negatives on one side of your battery. All right, so if we have equal concentrations, if it's not standard, we have to use our Q. Q is products over reactants. And so zinc 2 plus was our product. And Cu2 plus was our reactant. And these are solid metals, strips of metal, so they're not going to go into our equilibrium expression. If the concentrations on both sides are equal, in this case we said they were both 0.25, then the E of our cell, so our volts for this cell, will be the same for this compared to a standard. Just remember, when it's standard, you have 1 molar and 1 molar, okay? So standard conditions would be 1 molar concentration. If the concentrations are not 1 molar, but they're equal, then this number will not change. We put it into our Nernst equation to figure that out. Okay, what if we have the same cell, but we don't have our standard? So we said our reaction was this. I'll show you how to use the Nernst, and then I'll show you a much easier way. Okay, so this was our reaction. And so Our Nernst tells us the E of the cell not standard. Okay, so E of the cell equals our E for our standard minus RT over NF natural log of Q. Okay, this value right here is the one that we determined by taking the numbers, okay, at our standard temperature, using standard concentrations, 1 molar, 1 molar. These are the numbers that we took off of our reduction table, our reduction potentials. And so that's what's going to be your standard right here. And so we said that was 1.100. Okay, the R is our 8.314. This is on your formula sheet, and this is going to be in joules. Okay, this is going to be joules per coulomb. This is in joules. N is the number of electrons transferred. So what happened here is zinc lost 2, copper gained 2. So the overall transfer of electrons was 2 moles of electrons. Okay, and then our temperature, we're being told this is at 298 Kelvin. So the temperature is still standard temperature. What's not standard are the concentrations. They're not both 1 molar. And then obviously we could solve this using a temperature that's not standard. And then we have Faraday's constant, that's our F. This is on your formula sheet. Okay, and that's coulombs. So that cancels out this coulombs over here, or it subtracts it out. And then natural log of Q. All right, so our Q is our products over reactants. This is my product, the Zn plus 2. This is my reactant, the copper. And so we're being told, so we're going to do Zn plus 2 over copper, 2 plus or plus 2. And we're told that the zinc is 1. And we're told that the copper is 0.25. Okay, and so this is going to give us our Q value, and this is 4. Okay, so now we can go ahead and solve from our E cell, and that gave me 1.0822. Okay, it was 1.1, now it's 1.0822. So the cell potential, when we change this concentration to 1 instead of 0.25, that decreased. So the cell potential decreased. Okay, the cell potential decreased when the Zn2 plus, which we said was 1, increased. Okay, look what's happening here. We're adding in more product. Okay, Zn2 plus is our product. And so we have more on the product side. This is not equilibrium. It's simply a flow of electrons, a transfer of electrons. But we do have a positive and negative to account for here. So we have more of our products in our battery. And if we have more of our products, that's going to decrease our cell potential slightly. It's kind of like when your battery runs out. Okay, it takes some time, but that decreases the cell potential because we have more of these products. Just beware, it's not Le Chatelier. It's not equilibrium. Okay, we could do the same thing, but instead changing the copper. And we can imagine what's going to happen here. And so we had our reaction. Our reaction was Cu2 plus Zn, solid, forms Zn plus 2 plus copper. And we're using our Nernst, so we're setting this up the same way. So our E of our cell equals our 1.10 volts. I'm using the same exact numbers, minus our 8.314. This is on your formula sheet. That's in joules. This is also in joules, and this will be in joules, times 298. This will be joules per coulomb. A volt is joules per coulomb. 2 electrons transferred, Faraday's constant, natural log of Q. Okay, Q is products over reactants. So Q is Zn plus 2 over Cu plus 2. And so our Q in this case is 0.25, and this is 1. And so 0.25 divided by 1 is 0.25. And so when we solve here, we get our E of our cell not at standard conditions, and we get a value here that is 1.118. Okay, notice it was 1.1. And so what happened here was the cell potential increased. It's higher than the standard. And so the E of the cell increased when we increased our copper plus 2. Okay, why? Copper plus 2 is a reactant. So we're putting in more of our reactants. That pushes the electron flow forward. And so as a result, that increased our cell potential. So that's really pretty much it. They actually don't require that you use the Nernst. You can use it if you like, but the easiest way to look at it, if they give you a free response where you have to talk about standard versus non-standard conditions, it would be a good idea to use that formula to help you when you're describing what's happening. However, if it's a multiple choice, just know that if you're increasing what you have over here, that's going to increase the flow forward of your electrons. If you're adding more of this over here, that's going to increase the flow in the reverse. Okay, and so as a result, that will decrease the potential. And so Nernst actually isn't that difficult if you're able to look at it that way. Just understand it's not actually equilibrium, it's flow of electrons, and it's changing the amount of the reactants compared to the amount of the products. And so that's it. The last thing that I'm going to post is one short homework assignment. Make sure you do that practice test that I gave you.